Hello everyone, welcome to a lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at ComStates University, Islamabad, WA campus, Pakistan. The topic of this lecture is real and protected modes of addressing in microprocessor. These slides have been edited from the sources given here. To begin with, let me introduce the programming model of Intel family of microprocessors. The programming model is actually the internal architecture of a microprocessor. In the internal architecture, we need to understand the sizes and number of registers that are visible to a programmer. A programmer, when develops a program, he or she must know the registers available to use during the programs. So the registers shown here are the programmer visible registers. These are the registers that a programmer can refer to during the programs. While writing a program, a programmer must know the names and the size of the registers to use while writing the programs. These registers can be categorized as general purpose registers, special purpose registers, and segment registers. The general purpose registers are given here. These registers are general purpose registers. The first register that is used for different purposes is the accumulator here, and the accumulator can be a 16-bit register, or it can be a 32-bit register, or even it can be 64-bit register depending on the microprocessor used. In the 8086 and 8088 microprocessor, accumulator is a 16-bit register. This 16-bit register can be accessed as an 8-bit register as well as a 16-bit register. Furthermore, even if the accumulator is accessed as an 8-bit register, its rightmost byte, which is the low byte of the accumulator, can be accessed using the name AL, which means accumulator, and the low byte of the accumulator. So AL is normally used. If the higher byte of this accumulator is required to be referenced, then AH name is used to access the higher byte of the accumulator. In addition, the 16-bit part of this accumulator can also be accessed using the name AX. And when in the later microprocessors, where accumulator is available as a 32-bit register, which is the extended version of the accumulator, so the name for this 32-bit part of the register, when a 32-bit register is used, then the name EAX, which means extended accumulator, EAX name is used to access the accumulator. Similarly, for the base index register, the same naming convention is used, where the low byte of the base is accessed as BL and the higher byte of the base is accessed as BH, and the 16-bit register is accessed as BX. And if there is a 32-bit register, base register in the microprocessor, then the EBX name is used to access the 32-bit of the base index register. The same pattern goes for the count and data registers. And then there are other three registers: base pointer, and destination index and source index. Base pointer is normally used to provide offset address, which is actually added with the starting address of a segment, and then to access a particular address within that segment. Destination index is normally used with the string instruction to provide an offset address in the extra segment. Source index similarly is used with the string instruction to provide the offset address for the source segment, that is normally the data segment. So these are general purpose registers, and they can be used for different purposes. That's why the name general purpose registers is used. There is another group of registers which is called special purpose registers. As the name specifies, these registers are used for special purpose and cannot be used for general purpose. For example, the stack pointer register provides an offset address when the stack's memory segment is to be accessed. The stack segment register would provide the starting address of the segment, and then the stack pointer would provide the offset address within that segment. There is an extended version of the same stack pointer register as well, which is referred to as ESP, extended stack pointer. Then there is an instruction pointer register which provides the offset address for the code segment when an instruction is to be accessed from the code segment memory segment, which is called code segment. Then instruction pointer provides the offset address within that code segment. And there is a flags register. The extended version is called E-flags. Flags register contains different or stores different conditions. For example, the overflow flag, the carry, the auxiliary carry, the parity, and so on and so forth. So these bits would represent the current state of the microprocessor. There are segment registers as well. In 8086 and 8088 microprocessors, there are 4 segments registers. Code segment register, which is represented with CS, data segment register, extra segment register, and stack segment register. These segment registers would provide the starting address of the segments, the 4 segments within the memory. In 80386 and above, there are 2 additional segment registers referred to as FS and GS. The shaded areas here and this shaded area are available only in the 80386 and above microprocessor. The 32-bit registers, except segment registers, 2 additional segment registers F and G. These are available only with the 80386 and above microprocessors. The unshaded area, this white area, and the accumulator and tell flags register, and then from code segment to stack segment register. All of these registers are 16-bit registers in the 8086 and 8088 microprocessor. The extended version of these registers plus the FS and GS segment registers are not available in the 806 and 8088 microprocessors. In the real mode memory addressing, this is the mode used by the DOS operating system, disk operating system. This is the only mode available on the 8086 and 8088 microprocessor. Because only 1 megabyte of memory is available with these 2 microprocessors, there is the only mode available on these microprocessors is the real mode memory addressing. On the later microprocessor, both real mode and protected mode of memory addressing are available. In the real mode, the memory address is the 20-bit address. That means that only 1 megabyte of memory can be supported. There can be a 16-bit data bus. In the 8086, there is a 16-bit data bus, while in the 8088 there is an 8-bit data bus. There are 16-bit registers in both of these microprocessors. In the real mode memory, the first 1 megabytes of the memory system in the later microprocessors is used, and this 1 megabyte of memory is also called real or conventional or DOS memory. The later part of the memory in the later microprocessors is accessed when the microprocessor is operating in the protected mode. In the real mode, the 20-bit address is obtained by combining a segment number which is taken from any segment register, port segment, data segment, or extra segment, or stack segment, and an offset address which is taken from any other processor register is added with the segment number taken from the segment register, and a 20-bit address is created, and that 20-bit address is then called the effective address, effective memory address. In the real mode, the segment register address is 16 bits, and it is appended with 0 in the hexadecimal, or 0, 0, 0 in the binary, or it is multiplied by 10h in the hexadecimal, or it is multiplied by 16 in the decimal to form a 20-bit starting address of the segment. So each time a segment register is accessed, the 16-bit value taken from the segment register is appended with 4 zeros in the binary on the right hand side, or a single 0 as a hexadecimal digit on the right hand side, and we will get a 20-bit address, which is the starting address of the segment. Then the effective memory address within that particular segment is calculated by adding with this 20-bit segment starting address the 16-bit offset address is added with it, which is taken from another microprocessor register. So the 20-bit starting address, which is calculated here, is added with a 16-bit offset address taken from any other microprocessor register, and a 20-bit address is calculated, and that is the effective memory address. And this effective address is the address of the particular location inside that specific memory segment. For the 8086 microprocessor, the segment length is fixed at 64 kilobytes. The reason it is 64 kilobytes is because the offset address is 16-bit, and 2 raised to the power 16 is equal to 64 kilobyte, and the same principle goes with 8088 microprocessor as well. So the offset address taken from any offset register determines the maximum size of the segment, which is fixed at 64 kilobytes. So the segment, any segment in the real mode memory addressing is at fixed size, and that is 64 kilobytes. So each segment has the size of 64 kilobytes. Here we have an example how to create the effective address when the microprocessor is operating in the real mode. In the real mode, the microprocessor can use only 1 megabyte of memory if it is 8086 or 8088 microprocessor. And the only mode that is available with these microprocessors is the real mode. That means it can only support 1 megabyte memory, and that 1 megabyte memory can be used or can be accessed using real mode. So let's suppose this is the total memory. Here the starting address or the starting location is 0000H, means this is a 20-bit address, and all of the 20 bits are zeros. For simplicity, these addresses are represented using hexadecimal. So each digit in the hexadecimal corresponds to 4 digits in the binary. So this is actually a 20-bit address. So this is the first address of the memory, and this is the last address of the memory. So the total locations or the total addresses are 64 kilo. And let's assume it is a segment, a 64 kilobyte segment. It can be any segment. It can be code segment. It can be data segment. This is the starting address, or the physical memory address of this segment, which is a 20-bit address, or 20. It is a 20-bit address, or 5 digits in the hexadecimal system. And let's assume we have a segment register which for this particular example has the value 1000. This is again a 16-bit segment register. And to get the effective address, this segment number in the segment register is appended with a 0 in the hexadecimal. So if this is the segment register content, then an additional 0 in the as the hexadecimal digit is appended on the right side. So we would get a value which is 1 0 0 0 and 0. So this value is the starting address of the segment here. So here it is 1000, so it is the starting address of the segment, and this address is calculated by appending a 0 at the right side of the segment number taken from this segment register. Now this appending a 0 in the hexadecimal would give us the starting address of the segment, but we have to reach a particular location inside this segment. Let's suppose this is the location where the microprocessor has to reach. Then an offset address, which is an address relative to this starting address of the segment. So that offset in this particular example is F000 in the hexadecimal. So this offset address is actually the distance from this starting location till here, and to get to that location, the offset address is to be added with the starting address of the segment. So the starting address of the segment is 1000, and when F000, which is a 16-bit offset address, when this value is added with the starting address generated here, then we will get 1F000. So this 1F00 is the effective address of the byte that is to be accessed in this particular segment. The same address calculation is used for all the segments. If this segment is a code segment, then this segment register would be a code segment register, CS register, and the offset address F00 would be provided by the instruction pointer register. And if this segment is a data segment, then this segment register would be a data segment register, DS, and the offset address can be provided immediately, or it can be provided by the source index register or any other offset register. And similarly, if this segment is a stack segment, then this segment register would be a stack segment register, SS, and this offset address would be the stack pointer register. So this offset can be provided by the stack pointer register, SP, which is a 16-bit register. So in any case, when a particular segment is to be accessed, the microprocessor would access the segment register, corresponding segment register. A 16-bit value is taken, a 0 is appended, an offset address is added, and effective address is calculated. And that is the address where the microprocessor has to access. There are some other examples of how to calculate the effective address. Let's suppose we have to calculate the effective address EA. Then it is calculated by getting the segment register SR, and it is multiplied with 10H. This multiplication is equal to appending a 0 hexadecimal digit at the right hand side, or it is also equivalent to multiplying 16 in the decimal. So either way is correct. So segment register, the value in the 16-bit value in the segment register is multiplied with 10H, then an offset address is added. So this is the formula to calculate the effective address inside a segment. For example, let's suppose the segment register has 100H. This is the count 16-bit value taken from any segment register. 0 is appended at the right hand side. This 0 appending this 0 is equivalent to multiplying 10H with this value. And let's suppose the offset address in this example is 0023. So these two values are added, and the effective address that is calculated is 10023. Similarly, if the segment register content is A, F0, a 0 is appended, and let's suppose the offset address is here, then we will get this effective address, which is AB034. And if the segment register content is 1200H, a 0 is appended at the right hand side, and then the offset address is added, and we will get 21FF0, which is the effective address, effective memory address. There is a question: is 3FC81 a valid starting address of a segment? We have noted here in these three examples, 1000, this is the starting address of a segment, this is the starting address of a segment, this is the starting address of a segment. Each time the starting address of a segment is to be calculated, the 16-bit part of that starting address is always taken from a segment register, and a 0 is to be appended at the right side of their 16-bit value or segment number taken from the segment register. So each time a starting address is calculated, there must be a 0 at the right side of that starting address. So if we look at this address, there is no 0 appended at the right side. There is digit 1. So this is not a valid starting address of the segment. Different segments can be defined as overlapping. Let's suppose this is the memory as usual. All zeros, which is the starting address of the memory, and all F's, which is the final address of the memory. And three segments, code, data, and state segments, are defined by initializing these segment registers with these values. The code segment register has the value 090F. So the starting address of the code segment would be 090F0, which is here, 090F0. And if the content of the data segment register is 0A0F, then a 0 is appended here. So 0A0F0 becomes the starting address of the data segment. 0A0F0 becomes the starting address of the data segment. And similarly for the stack segment, that is the starting address of the stack segment. Now let's assume that the top up code segment can be calculated. As we know, each segment in the real mode is fixed. The size of each segment is fixed, and that is 864 kilobytes. So each segment has a size 64 kilobytes. To find the final address of a segment, F, and F is to be added with the starting address of that segment. So by adding F with the starting address of the segment, we will get the last address within that segment. So in this example, when the code segment has 090F, as 0 is appended, so this will become the starting address of the code segment, and the maximum limit, which is FFF, is added with this starting address. We will get 190EF. 190EF is the final address or the last address of the code segment. In this memory map, these three segments are overlapping, which can be seen here. The code segment, the data segment begins within the limit of code segment. Stack segment begins within the limit of data segment as well as code segment. So all of these three segments are overlapping. That is, some part of the code segment is also part of the data segment, and some part of the data segment and some part of the code segment are part of the stack segment. So these three segments are overlapping with each other. We must be careful that the code should be limited to only the non-overlapping part of the code segment to avoid offset of segment overlap. To protect code from overwriting, code should be stored or used only in this part of the code segment. When code is stored in the overlapped part of the segment, then that code can be corrupted. It can create problems. So it should be one should be careful to store code only within this part of the code segment, and it should not be stored in the overlap part of the code segment. There are some defaults. Some segments are used with default offset registers or offsets values. Code segment is used for programs or code. Stack segment is used for the stack. Data segment is normally used for the data. Extra segment is normally used for the string as the destination. And when string instructions are used, data segment register is used as the source of string. Default offset addresses that go with them. For example, with the code segment, the effective address calculation is done by adding code segment register content plus the content taken from the instruction pointer register. So this code segment register will provide the segment number in the segment register CS, and this IP, which is the instruction pointer register, would provide the offset within the code segment. So this is the format to write CS colon IP, and this is written in the brackets. So the content taken from the code segment plus the content taken from the instruction pointer would give us the effective address for the code segment. There are other segments and there are some default offset addresses. For the code segment, as we saw here, instruction pointer in the 8080, 8086, 80286, the 16-bit offset address is provided for the core segment register from the instruction pointer register. In the 80386 and above, when 32-bit offset is used, EIP or the extended instruction pointer is used. The purpose of the core segment is to store programs. For the stack segment register, for the stack segment, the segment register is stack segment register, and the offset address is provided by the stack pointer, base pointer, and the extended version are ESP and EBP. And the stack segment is used for the stack. Similarly, the data segment register is used for the data segment, and the offset address can be provided by a number of registers, including BX, destination index, source index, 8-bit or 16-bit immediate value, and if we need 32-bit offset, then the extended versions are used. And the data segment register and the data segment in particular is used for the data to store. Extra segment, DI with string instructions is normally used for the offset address. EDI when 32-bit offset is needed, and this is used for the string destination. Segmentation has pros and cons. The advantages of the segmentation include that they allow easy and efficient relocation of code and data. The code and data can be relocated anywhere in the memory. To relocate code or data within the memory, only the number in the relevant segment register needs to be changed, as the addresses inside any segment are relative to the starting address of the segment. So only segment starting address is to be modified, but not the offset addresses within the segment. So data or code can be located to anywhere in the memory, and it will not affect the functionality. These features or these advantages have some consequences. A program can be located anywhere in the memory without making any changes to it. When a programmer writes a program, the programmer does not need to worry about the actual memory structure or the map of the memory in the computer. So the programmer just writes the programs, and during execution it is not a problem where the program is being loaded. So a program can be loaded at one set of addresses today, and it can be loaded in different location tomorrow in the memory, and it is not a problem. And this is called relocation, and this relocation of the programs and data is achieved using the segmentation. So the segment registers are used for this purpose. This segmentation has some disadvantages as well. It requires complex hardware to generate the memory addresses, to append zeros at the right hand side, and then to add the offset address to calculate the effective address. So it requires complex hardware. Address computation requires some delay. Each time a memory address, each time a memory is accessed, an effective memory address is to be calculated, and it requires some computation, which would create delays. Also, there is a software limitation as well. The program size is limited by the segment size. You cannot write programs, large programs, because each segment has a size of 64 kilobytes. So for the 8086, a segment can be up maximum 64 kilobytes. So it would limit the size of the programs. for these microprocessors. Furthermore, segment size is fixed and is at 64 kilobytes. So this is a limitation. You cannot define segments of a small size. You cannot define segments of large size. So segment size is fixed at 64 kilobytes. And segments cannot begin at an arbitrary memory address. For example, 3FC81 is not a valid starting address of a segment, and this is because the segment register provides the 16-bit part of the 20-bit memory address, and this 16-bit segment number is appended with a 0 at the right hand side, and that 0 would not allow us to start a memory segment at any arbitrary location. Each the starting address of any segment must contain a 0 at the right hand side. So a segment cannot begin at an arbitrary memory location. With 20-bit memory addressing, segment can only begin at addresses starting with 0h or at 16-byte intervals. So when a segment is defined, the next segment can only be defined at 16-byte interval. So principle is difficult to apply with 80286 microprocessors and above because the segment registers are still at 16 bits. The segment registers are only at 16 bits in 80286 and above microprocessors, just like the 8086 and 8088 microprocessor. So the segment registers are still 16 bits, while the memory that it can support increases from 1 megabyte. So the later microprocessor can support more memory, while the segment registers are still 16 bits. So 80286 and above use 24 and 32-bit addresses, but still the segment registers are 16 bits wide. And no protection mechanisms is used in the real mode. Programs can overwrite operating system code segments and can corrupt them. When programs are allowed, or if it is possible for the programs to write operating system's code, then the system can crash. So use memory segmentation, but in the protected mode is the ideal alternative. Segmentation are good, but with some modification to aid the feature of protection for the code. And this would give us a protected mode of segmentation, where primarily we need flexible definition of segment starting address. Any segment should be allowed to start at any address inside the memory. Also, the size of the segment should be flexible. It can be of any size. The segment size can be small or can be large. It should be allowed. Also, there should be a protection mechanism to prevent programs from corrupting the code and data of each other and of the operating system. So these are the three features that we would like to have in the protected mode. So segmentation is good, but these features should be added because they are good features. The segments, they are flexible. The segments can be defined at any location. They can be of any size, and there is a protection mechanism is added. And these features can be achieved using the protected mode of memory addressing. And we will discuss this protected mode in detail in coming lectures. But briefly, this protected mode of memory addressing is the mode where the Windows operating system operates. Uh, in 32-bit addressing, 4G of memory with 2G for the system and 2G for the application. Protected mode still uses segments and offset addresses, but in a different way. Segment definition is through a more complex selector and descriptor mechanism, which provides greater flexibility relative to the size and the location inside the memory. Offset address 16 bits for the 286, and the offset address can be 32 bits for the 386 and above microprocessor. For example, the offset address can be provided by the extended and instruction pointer register. Descriptors are placed in the descriptor tables and the main memory. Protection is provided by restricting access to memory segments through the privilege levels and the access rights. Further detail of the protected mode of memory addressing would be provided in coming lectures. If there are any queries noted in this lecture, please write them, and you can ask those queries and questions during the online session. Thank you.